Okay, so hello everybody, I'm Oleg, and today I will be talking about a little bit of history. So there is a common perception that history is like everything is improving gradually, and with every day everything is getting better. And most of the time it happens like this. But sometimes something happens, then some part of collected knowledge gets forgotten for some time, and then after, when time passes, it gets either rediscovered or reinvented. And I'll be talking about. So my talk was inspired by two things. One of them was a talk at FOSDEM this year at a history track about like alternative histories, and so the main idea was exactly like this: that there are sometimes something happens that some old knowledge gets forgotten and then rediscovered. And another thing that inspired me is an article by Dennis Ritchie about history of C programming language. And I decided that it would be interesting to combine these two things to just to describe just one instance when there is some kind of old knowledge that gets partially forgotten and discovered later. So what? How this happened? In the end of 1960s and beginning of 1970s, there were mainframes, big computers that were occupying like large rooms. So, for example, this room, maybe it would be enough for one mainframe, maybe not. I don't know. It depends on the exact model. Most of the development of hardware and software was happening at mainframes. And at the time, they had quite advanced hardware. So they already had 32-bit addresses. Actually, in IBM 360, only 34 bits were used. By on IBM 370, already 31-bit was used of the address. They had quite intelligent peripherals with their own processors and stuff like that, like we have now, by the way. And software was advancing pretty quickly at that time. They already had hypervisors, virtual machines. That's all the hype today. It was invented quite long ago. And there were quite powerful programming languages. There was significant development in programming languages during very short time. But they had one drawback. They were very, very, very expensive. So only big organizations would be able to afford these mainframes. So they were at large government organizations, they were at huge companies like IBM would afford to not only produce but also to own some mainframes. But they were not affordable to smaller organizations. And this void was filled with minicomputers. Minicomputer is a smaller, more affordable computer. It was maybe looking like a couple of shelves, an additional shelf for these tapes. They were more affordable, not as like affordable like a laptop now, but still affordable to some medium-sized organization. But they were really underpowered compared to mainframes, and choice of software was quite limited. How underpowered? Let's take a look at PDP-7. PDP-7 was introduced in 1964. It had 4K 18-bit words. That is rough kilobytes in modern units, but they're not directly applied here because there were no bytes. And the word was minimal addressable unit. So not address was you would not be able to address smaller pieces of this word. Bell Labs had some of this PDP-7 computers, and when they pulled out from a Multics project, it was quite interesting and ambitious project to design multitasking advanced operating system for quite a bigger hardware. A small team started working on operating system for this PDP-7, and they just fun called it Unix. This is not this, I think it was how it was called at that time. They were writing software on assembly language, but it was not very convenient, so they decided to have some programming language that is combines power of assembly with convenience of assembly. So the B programming language was designed as a result. B programming language, it's said that it's some kind of descendant from BCPL, but it uses some ideas from BCPL, but it's completely different. It's typeless programming language, so the only data type it has is Word, 36-bit Word, to be precise. No floating pointer arithmetics, and interesting feature, it still has arrays, but not as a separate data type. So this definition declares A as a variable of word type, initialized with address of memory containing 10 words. So it's in modern terms, like if you compare to modern C, it's like declaring pointer to character and initialize with string. Here's the example program. You can see that it's quite similar to C. Oh, I'm sorry. Okay. I'll move a little bit here to not obscure this. Okay, so this is an example program. You can see that it's quite similar to modern C. Similar function definition. The only difference is that it doesn't have type, of course. The variables declared as external, because you still have to declare variables, but you don't need to specify type. And here are these variables defined and initialized. And by the way, this kind of syntax without equal sign existed in early versions of C as well, by the way. So the only difference is very few difference. External words is a little bit different. No equal sign initialization and no types. And by the way, bootchar actually is outputs the whole word. So you have to pack characters inside these words, like you see here. The compiler of this language was designed to be as simple as possible, to fit into memory of PDP-7. So they were using cross-compiling before, but they decided to run it natively. And the language is quite basic. It has very simple parser, very simple code generator, and then PDP-11 has come. So in 1970s, so PDP-11 was introduced in 1970. It's still mini-computer, but much more powerful. It has already 16-bit addresses. It has 8-bit bytes. It has an interesting feature called orthogonal instruction set. This instruction set is quite logical, and for example, before there were several instructions for loading to register, for storing from register to memory, stuff like that. In PDP-11, you have just move instruction and different addressing modes for moving. So you can use the same instruction for moving between registers, from register to memory, from memory to register, or from register to some place indexed by some place in memory and stuff like that. So later it got MMU, memory management unit, so you could run multitasking time sharing operating systems. It didn't have dedicated instructions for input-output, but it had universal bus, actually two types of buses, minibus and Q-bus, and some special area in memory that was used by input-output registers. It was quite popular, so popular that it was widely known in Soviet Union. Yeah, it was
improved on your machine. Some of them were really good. Some of them were
yeah. And one of these computer, so Bell Labs decided to buy one of these mini computers in 1970 and started porting Unix to that, or what was Unix at that time. And this is how C programming language was born. So it was based on B programming language, and the goal was to preserve as much compatibility as possible with B programming language, because there was already some code base written in B. Not as much by modern standards, but still. So the main syntax of C remains the same, but PDP-11 has different architecture. It has bytes, it has words, and the size of the address and the size of the minimal address unit are not the same. So they had to introduce not only integer type but also character type. And then, okay, here's the problem. We have different types, so we need to have different pointer types, because pointer arithmetics was used quite extensively in B, and we really need to have like this pointer +1 to be pointing to the next word, not the next byte, if we're working with words. Then here came another problem. C needed real arrays, because this like pointer initialized to some area in memory is quite nice if it's local variable, but what if you have it as a member of a structure? How can you store a pointer in this structure? The structure needs to have array itself. So in C, arrays turned from just pointers to real arrays, but decaying to pointers when you use them in expressions. So the name of array is turned to pointer automatically if to pointer to its zeros element. So syntax for declarations remained mostly the same, with the only difference that the type was added. But if there is a type, there is suddenly need to more complex types. For example, it can be array of pointers, pointers of arrays, pointer to pointer, and so on. So it led to syntax like this, more complicated one, like expression syntax, expression-like syntax. Of course, structures were added. There was some time when C didn't have structures, and the first attempt to port Unix without structures has failed. And of course, C preprocessor that allowed to separate declarations from definitions, stuff like that, and do lots of inventive things that are considered hard now. Gradually, C was improving from very primitive language with almost no type safety. It gained little bit stricter controls on what you use, how you convert pointer to integer, and vice versa. It got unsigned types because before that, the only way to do unsigned arithmetics was pointer to char. It's unsigned. It got casts from one type to another. And by the way, it got each structure got its own namespace for its members. Before that, the name of a structure member was global. It was just an offset. And artifacts of that you can see in some Unix interfaces. For example, if you look at struct stat, all its members start with st underscore member names. Why is that? Because it was address space was namespace for member names was just a single one. And by 1989, there was a C standard that improved C even more. For example, it added argument types to functions, because before that there was no checks for that. It added a void keyword and stuff like that. So, and from that, further development of C and then C++ and other C-like languages started. And then, what happened is that there was another, but at the same time, when minicomputers were becoming more and more popular, the attention shifted to them. And significant development of what was happening in mainframes started to get not exactly forgotten, but it was not applicable to minicomputers because all these advanced programming languages were too advanced that their compilers were not fitting into the memory of existing minicomputers. And by the time when they started fitting there, there were already minicomputers had already their own ecosystem based on C language. So yeah, and after that, actually another shift happened when minicomputers were replaced by personal computers. And if you remember first personal computers that had single tasking operating systems, also very underpowered, but fortunately it was not too much knowledge was forgotten at that place, because you know when IBM PC became popular, it already had 640K of memory. It's not like 4K words at PDP-7. So I remember like there were some. So C programming language was able to move to personal computers relatively safely, and C++ as well, without losing too much. And also GCC helped quite a lot because it became so portable compiler that every new from some point every new architecture was getting to GCC first. Okay, so that's about what was happening at minicomputers. Meanwhile, in another reality, like mainframes, there were different other programming languages, much more advanced at that time. And I will briefly describe three of them. There were much more, of course. But this is how progress in programming languages was progressing when there is enough resources to run big compilers. So, Algol 68, Clue and other. That's just three examples of languages I selected just because I like them. But when I started working on this presentation, I found that these are the three languages that creators of C and C++ admit to have biggest influence on them. Okay, Algol 68, quite nice programming language. It was introduced in 1968, quite long ago. Then revised report was released in 1973. Revised report on Algol 68 is quite a big book, written by Van Wijngaarden. It's actually it's formal description of not only syntax but of all the semantics of this language. So if you find this book, don't read it. Your brain will explode.
It makes great door stuff. Door opening stuff.
You don't usually read the door stops, right? But it's from a historical point of view, it's actually a great book. It's a legacy of computer science. And when I was working on this presentation, you know, when you're looking at Wikipedia article, sometimes you follow random links, and I found a link to a Soviet GOST. GOST is a statewide standard for Algol 68. It was a PDF file that is actually scanned some printed document with not very good quality. I downloaded it and took a look. It's in Van Wijngaarden's revised report, translated to Russian, completely, with all keywords. So this revised report became a statewide standard in Soviet Union. Okay. Anyway, so nice features from Algol 68. It's one of the first, maybe even the first language that has orthogonal design. That means that it has designers of this language tried to have as less concept as possible, but they can be combined with any combination. So, for example, in Algol 68, there is no separation between statements and expressions. Every statement is an expression. And here are two examples. And these two examples are essentially x and y are initialized to, are assigned to exactly the same values. So the second form is just shorthand for the first form. Second thing is that variables are references. So if you declare a variable like this, it's just shorthand for declaring a variable like this. And by the way, if you see equal sign instead of colon, it means we are declaring a constant. So x and y are constant of reference of type reference to it. And Algol 68, yeah.
You
Is x initialized to 0?
No, undefined. No, x is not initialized. X is declared as a constant of the type reference to integer, and it references to some local, to some place on stack that is not initialized. If you want it to initialize to initial value, use syntax like this with assign operator. And if you use equal operator, you're declaring constant. So this one and this one is exactly the same. X, every variable is a constant of reference to something. If you want to have a reference that you can assign, then declare a variable to be a constant of type of reference to reference to something. So if you add the word ref here, then you'll do exactly this. Then, Algol 68 has first-class functions. This means that type of like function, actually it uses the word procedure for that, but anyway. So a function taking these arguments and having this return type, it's also a type. And when you declare, if you declare a procedure or function with name, the syntax is the same as declaring a constant. Algol 68 has a very advanced operator overloading. It means that you can not only overload meaning of existing operators, you can invent your own operators and your own keywords. The only limitation, I think, that the new operator should not start with open parentheses.
Of course.
Here's example program. Very simple. So, hello world program. I didn't. I only did example for C programming language because everybody knows that. But for Algol 68, it looks like this. Very simple. And by the way, it's a comment. But I like Algol 68 so much, so I added another example program doing exactly the same. Here you see two interesting features. First, begin and end are exactly the same as open and closed parentheses, because everything is expression. Yeah? Double parentheses, yes. Because print function has just one argument. There is nothing like argument packs in Algol 68. It has just one argument, but this argument is a flexible array of unions.
Also, it's expression.
So
it's expression. As you told, everything is expression.
Yes. So print is also a function that returns some value. I think the type of this value is just void. But anyway, the outer open, the outer parentheses are just how function arguments are passed, and the inner ones is a constant of type of array. Okay, so that's double parentheses are required. But if there is only one argument, then you can pass just one argument. And here's what's happening here. So you see it's format out, and you see very familiar function name, right? Printf. Where did it come to C programming language? From Algol 68. And in Algol 68, they have a formatted input output, but they have format is its own type. It's not a string. It's its own type, and it uses dollar signs instead of quotes. So this means that literal string hello world, and then new line. Well specifier means new line. This is quite interesting because format as its own type allows to somehow recompile formatters. But anyway, so it's quite interesting programming language. It really has quite orthogonal design. Then
Common symbol of
it's a self symbol. It's another way to denote comments. You can denote comments with hashes, with send signs, and with core keyword.
Because the use of the various symbols was because of the assembly language stuff we used underneath, and people were familiar with that. That's why they call them different types of.
You mean send signs? Oh, okay, that's it.
I think because a lot of machines at the time had same time signs. Maybe for some of the other operators, they have like really elaborate mathematical symbols, which they took from APL. But I think every implementation was sort of, to some extent, free to map it onto their own character setters. These lines had sense on sort of APL characters.
Yeah, and by the way, in Algol 68, do you think that this is syntax highlighting? No, it's not. These are keywords that are not reserved ones. Okay? So you can have a variable called int, but it will not be called. Okay? Yeah, that's quite interesting because how can you enter both on their keyboard? There are different ways to enter keywords in Algol 68. One of them is a dot before the word, another is apostrophes around the word, and the third one is uppercase, but then you will have to have reserved words. But anyway, it's implementation dependent. Okay, another interesting programming language is Ada. It was a little bit late to the party. It was introduced only in 1983, when C already was formed in the way it's described in first edition of Kernel and Ricci. But this language had significant influence on anything else. It's more like a Pascal family language. It has a very strong typing system. So, for example, you can't convert integer to float as easily without explicit conversion operator here. It has modules. It has built-in high-level multitasking facilities. And it has exceptions. It has generics. Not exactly as interpreters in C++, but close enough. Closer to generics in Java. Anyway, it has a greater overloading. Not as wild as in Algol 68, so you can overload only a specified set of breaks still. And here is an example code, just to give you a taste that it uses different, so it looks different but still familiar.
And it was invented by
No, it was invented by a big committee. There was some kind of this is a language that was designed for Ministry for Department of Defense of the United States. There were four competing proposals called red, green, blue, and yellow. Then two proposals were eliminated. The final was red and green, and as a result, green has won, and it became Ada programming language.
It was named after Countess Ada.
Yes, of course.
Yes.
Yes.
The guy who designed the winning was French.
Oh, yeah.
Yeah.
Yeah. So, and speaking of languages invented by a woman, Clue, Barbara Liskov. This language was introduced in 1975. It has a concept of clusters. So cluster is an abstract data type that has internal representation and that exports methods or rather functions to work with that. You can access this internal representation only through this explicitly defined interface. It has parameterized clusters. It's almost like templates, like in the sense that something in between generic templates. Clusters can be parameterized with a type. It has the concept of iterators. So if you learn Ruby or Python or wondering, wow, what a wonderful concept of iterators was invented there, how it was not invented there. It has interesting feature. It has exceptions, but it's not exceptions for exceptional use. So you can exceptions are for normal flow control there. So there we had
just like Python.
if you can compare efficiency of Python, yeah, but on the modern hardware, who cares? Yeah, so we can do for normal flow control like the file and that's the exception. By the way, in ADA, in standard text Algol library, and the file is also an exception. But anyway, but these exceptions are quite funny. They're because you have to somehow handle that. If you on each level you need to either catch this exception or rethrow or resignal, as it's called in Code. Then, otherwise, it leads to some horrible condition that causes usually program termination. So it's more like no except clause in modern C++. Yeah. Anyway, so also it has type-safe variant types. Actually, Algol 68 also has discriminated unions, but Clue is has much more type-safe way of handling these variants. It has automatic memory management, so it's mostly like Java. Everything is referenced there. It has operator overloading, but looking not like in C++ or in Algol 68 or in ADA. It's more like operator overloading in Python or Ruby, because in Clue each operator is just syntactic sugar for all of function with some specified name. So, for example, this is assigned to an array element, but it's a syntactic sugar for this construct. If you find this construct funny, just imagine that we have angle brackets instead of square brackets and two columns instead of dollar. Like in sorry. Yeah, like in C++. So this syntax is run this procedure from this cluster array parameterized with int type. And here's example problem just to give you a taste how full program, minimal full program in Clue looks. Nothing surprising except this funny syntax for procedure from a cluster. Some interesting side note that I think it would be interesting to make. It would be interesting to make is that currently we got used to that class is structure and class is abstract data type. Because in C++, structure was conveniently reused for object-oriented programming, and structure and also class is used for abstract data types. But it's not necessarily should be the case. So what is the difference? Abstract data type. It has some hidden structure and exposed interface to access this. So it's a data type, but it has hidden structure. Don't confuse with abstract class in C++. What is object? Object is about interface in Java sense, and constructor that creates a concrete implementation of this interface. But it should not be abstract data type at all, by the way. And it's not necessary that it will be implemented as a structure with data members. And structure. Structure is a convenient way for storing multiple data members in one namespace and in one place. But it's not necessary that object or even abstract data type should be implemented using structure. And here is how clusters are defined in Glue. In Glue, cluster is abstract data type. It has internal representation, but it doesn't have data members in the sense of C++ class. It just has internal representation. It can be a structure, an array, anything. So it's not a structure, and it's not an object because it doesn't have any inheritance. It's a virtual methods. Here is, can you see here, that some example of how a parameterized cluster could look. It's incomplete definition because I omitted some of the methods. Look here. Rep defines internal representation. Here it's array construction, by the way. Then we have some methods create that creates. Okay, I use the word method, but it's not method in the sense of C++, because in C++ a method must have an implicit member of the class, explicit argument of this class that is would be this inside this method, unless it's in Clue, it's not necessarily the case. So imagine that it has only static methods in C++, in C++, the language describing how C++ works. For example, create doesn't have any argument. Insert has argument. So rep is internal representation, CT is external representation. Then elements is iterator. You can see how iterator definition looks. Very similar to Python, isn't it? It has a yield iterator. So it implements a loop, and every time it yields a value, it just yields. And by the way, here we can see how iterator is used, because representation array also has elements procedure. And here's another interesting thing. Definition of procedure, but only if type T has some property. So there are two, it's a deep copy and this is shallow. And deep copy requires the type this set contains to have a copy function. If if this condition is not met, then there will be no definition for some particular type. Okay, so and then after so these languages, although 68 had a clue, are almost forgotten now. There are very few places. I heard that there is enthusiastic community around Ada, and I found out about that only at Postdem this year. But we never heard about the community around almost 68 or clue. So many ideas from these languages were not exactly forgotten, because guys working on C and C++ are quite literate in computer science, so they definitely were aware of these languages. And many of these ideas were restored and reused later, but in different form. So, what was restored pretty quickly? Of course, stronger type system type checks for argument types, void type that came from Algol 68. In Algol 68, everything is an expression. What about an expression that has no value? Of course, no problem, it has type, void type. Then references came to C++ in the early development when C with classes has joined into C++. And there was an anecdote of how it happened. So Bjarne Strausstrup was sitting with other guys at NT Labs in some room, and he was talking about that, okay, we have a problem. Like I want to have operator overloading, and I want like user-defined classes to look like built-in types. So it would be great to have overload for assignment operator. But everything is passed by value in C. So how can we pass the left argument? If it's passed by value, then you can't assign to it. If you pass by pointer, then you have to put ampersand before a variable name. This is ugly. So how can we solve this problem? And that McElroy said, but in Algol 68, and then Bjarne Strausstrup just stood up and ran out of the room.
You ran out of a lot of rooms.
So this is how references were adopted in C++, but not in the same form as in Algol 68, because in Algol 68, these references are fully usable as pointers in C and C++. With only difference that in Algol 68 there is no explicit memory allocation and deallocation, so it uses garbage collection. Then constants came to C++ about that time, but also in different form. And in Algol 68 you can define something as a constant or as a variable. But constants is not part of the type. So you can have reference to const, reference to something. So I would argue that in C++ constants came to slightly improved form. Templates. The most basis for templates was already found in clue. And C++ adopted it almost as is from clue. But then some interesting additional feature was added called explicit specializations. And then, for example, I don't know, we want to have vector type, but integer that just stores values in contiguous part of the memory. But for, I don't know, for Boolean values, we want to back them as bit stream. Okay, no problem. We have mainframed for any type T, but for Boolean we have different implementation. This is explicit specialization. It can be full specialization, partial specialization. For example, we probably want to, I don't know, store some pointers to any type in some special way or whatever. But sometime after that, some guy discovered that this sounds like functional programming to me, and he wrote a program that computes prime numbers at compile time and prints them in error messages. Then another guy came and improved that it's not necessary to use error messages for that. You can do this without any errors. So it was discovered that templates are functional programming language that can do any computations at compile time. Okay, templates came to C++ a little bit later, when C++ 2.0 was released, or to be precise, update to C++ 2.0 was released in 1991. So it was, I think, after annotated reference manual. Exceptions. Exceptions came to C++ almost in the same form as they are in Ada. I mean, semantically, not technically. But C++ became quite fertile ground for exceptions because it already had destructors. So having constructors and destructors allows very easy to have exception safe code. Just allocate everything in constructor, allocate everything in destructor, and you'll be happy. And bool type. That's surprising that it came so late to C++. Also came from Algol 68, by the way. Before that, just normal int was used for Boolean values. And as a legacy, bool is still a numeric type. And there are multiple problems because of that. Now, so these things were adopted by C and C++, mostly C++, relatively quickly. But there are some things that took much more time to get back. First class functions. In C you can have qualitative function, but you can't have a literal function. So here, how it looks in Algol 68. Here is literal of function type. Essentially, these examples are the same. There is a function that takes integer array and applies function to all elements and assigns a result of this function to respective elements. And this is how we call it. And by the way, interesting feature from Algol 68 is that you can have spaces in identifiers. In C++, please, you have underscore for that. And by the way, extended character set multiplication here. And operators lower bound and upper bound. Because in Algol 68, indexes of array are not like 0 to something. They're anything from 1 to 3, for example, here. In C++, we had to wait until C++ 11 for introduction of lambda expressions that can be used for that. Of course, it can be argued that lambda expressions are more advanced because they are not just functions. They can capture some variables, work like closures, and they are or looking like objects of some class with some anonymous name. But anyway, so it took just 43 years to come back to C++. Another feature that came back, but not exactly in the same form. So if you see at C++ 17 example, this is new syntax allow you to declare some variables in, for example, if statement, and then use them in it. It never was a problem in Algol 68 where you could have anything, anywhere, because everything is an expression here. And semicolon is just a way to write several expressions in sequence. You can write declarations, you can write any statements inside the condition of if statements in Algol 68. So this thing, it took 49 years, but not exactly in the same form. It's some limited, only in some special case you can use something like that. Oh, just one, sorry. Yeah. Okay. Then, some things that didn't yet come to C++, but can probably come in 2020. Concepts. In Glue, we already were able to specify additional restrictions of a type. So, for example, this is just a small part of the definition of a parameterized cluster set from an example before. Take a look at this where clause. This means that the set is defined only for types that have this condition met. And look at this definition of this procedure, that this definition is valid only for types that have this condition met. In C++ 20, the first condition can be expressed concursively because C++ 20 is not a standard yet. It could probably look like this. So you define a concept called equality comparable, and then you define your template requiring this type to be equality comparable. Or maybe I got wrong with this syntax. Maybe it should be like requires something. But anyway, I'm not sure about this syntax. 45 years, maybe more. Modules. Not only Ada had modules, many other languages had modules before. So what is a module? Module is a way to define something that exports some only these names and nothing else. In C++, we use just files for it. And if you don't export something from this file, okay, don't write this in input file. But nothing prevents you from polluting namespace for linking. If you don't place something in input file, but still place some externally linkable name in your implementation file, you have problems. So this is syntax for Ada. You can see this is a declaration of module or package in Ada terminology, and this is definition. So this can be separated. In C++ 20, you can add something like this. So this is just some module that has function f that just gets its argument. But look at this part. In other module, you can have code that is executed when module is initialized. That can be any code. Yes, similar. Yeah. And in C++, if you want some initialization code, okay, you can add this to some constructor of the global variable, much more boilerplate. So maybe 33 years if it's added, if modules are added in C++ 20, maybe more. And then for the completely set part, something. Last one. High-level mode testing. We don't. So this is an example of buffer task in other. It just implements circular buffer where you have two operations: insert element into the buffer and take elements out of the buffer. Elements of integer type. You have two edges for this task, and you can call these edges using normal syntax like buffer.insert, buffer.take, and stuff like that. And here's the body of the task. So it so this select does like entry is something a way to run the code to request a task to run some code for requesting. And this is the code that is run for insert, and this is code that is run for take. But they are guarded by conditions. So if somebody requests take, but the buffer is empty, the caller would be just waiting. So this is called asymmetric rendezvous. It's interesting that there's candidates for other programming languages, like blue and yellow had just semaphores and stuff like that. Red had monitors. It's like modules where there is synchronized access to procedures from this module. And in green, there was this asymmetric rendezvous that was selected because it's a higher level mechanism than all others. Fortunately, in C++, I'm not aware about something that can be as high level as this one. We still use mutexes and stuff like that, and I don't see how it can change in the future. In other languages, there is all hype about Go and its Go routines and channels, but it's still more primitive way than it was in Ada. So, so this is part of the knowledge that was not exactly forgotten, but somehow lost. We still remember about that, but we can't use it.
Sorry, what's stopping like conditions and premises there?
So what was
multitasking?
Hmm?
Like multitasking. Multi-threaded access to things, or
okay, so in Ada, task can be implemented as a thread, or Ada runtime can have its own scheduler to for its own task scheduling. So it's not one task to one thread. It can be more complicated and more efficient, by the way.
What our experience was permitting like that?
What? I'm so sorry?
So the experience of having C++ 3 and permitting is having C++ 20, and you combine the two together and get exactly what you got there.
Big problem with all these things is putting them into a language. Because how are you going to get uniform implementation across multiple machines? There's different. The thing about it is that if you have a number of different machines,
anyway, so this is part of the language. It's quite high level part of the language. And I'm afraid that without a language that allows to define not only class templates, but also its own language constructs, we can't do this library only. So that's the problem here, I think. And of course, we need some verification at compile time. Because if there is a deadlock at runtime, it's already too late. Okay, so here I was thinking about adding a slide about like moral of the story, but decided that not to do because I'm not sure what the moral of this story is actually. But anyway, like maybe like more knowledge, more grief, or something like that. Because when, like after learning all these interesting advanced programming languages, every time you encounter a new trendy programming language and start like, wow, maybe it has some interesting concepts I never heard about. And then,
when Go came out, there was a guy who wrote an article comparing Go and all the exciting features to another language which he didn't name, and at the end he revealed that it was Algol 68. I kind of showed how for all these sexy features in Go, you do pretty much exactly the same thing in Algol 68, almost exactly the same syntax.
oh yeah,
It's the same people.
So I think one of the things that came out, at least for me, was like heard some of these before, is that languages like Ada and Algol 68 were designed quite complicated up front, whereas something like C++ sort of accrued complexity over the space of decades. So maybe the trick, if you want to make a great language, is to kind of slowly add little bits, piece by piece, with all the craftiness that comes with that.
It would actually, I was thinking that it would be quite interesting if language like C++ was based not on C, but rather on Algol 68. No, Algol 68 is quite.
I'm going to suggest that I have the misfortune to be probably one of the older in the room here. And I had the misfortune to use the first commercial C compiler, which was written by a company called Mark Williams.
Compiler of Algol 68?
No, of C.
Oh, C, okay.
And you could literally put a book into it and choose problems.
But by the way, have anybody here was ever writing a program on Algol 68? Raise your hands. Okay, and me as well. Yeah.
Algol 60 pound.
Yeah.
That's Algol 60 pound.
No. but it's a completely different language, but it's interesting to hear that. Yeah. Did anybody ever write a program in Ada?
Does hello world count?
Huh?
Does hello world count?
What? Sorry.
Does hello world in Ada count?
Yeah.
Okay.
Cool. Okay, and now what about Clue?
I've seen programs in it that we did actually study at college, but I don't think it.
Okay, have anybody here heard about Clue before this event? Oh, that's interesting. Cool. Okay, that's great. So, yeah. So the moral of the story is left up to the listener of the story. And now the most excited part. Do you have any questions?
Could we maybe ask questions later because we're just kind of on schedule?
Ah, okay, sorry.
Sorry, not to cut it off, but yeah, maybe catch up later.